On April 9, 2025, in the prestigious journal Nature, scientists from Chalmers University of Technology unveiled a revolutionary piece of technology, a laser amplifier that could transmit information 10 times faster than anything in use today. Not faster because it breaks the speed of light, physics still holds firm, but because it broadens the bandwidth, the range of light wavelengths that can carry data, allowing more information to move simultaneously. Think of it like adding 10 extra lanes to a data highway. The result? A dramatic boost in data transmission capacity without needing to dig up and replace the vast network of fiber optic cables that already wrap around our world. At the center of this breakthrough is Peter Andriksen, a professor of photonics and lead author of the study. Andriksen and his team created a high-efficiency optical amplifier that expands the usable bandwidth from 30 nanometers, standard in today's telecommunication systems, to a jaw-dropping 300 nanometers. This means instead of sending data through a narrow tunnel of light, we can now flood a vast corridor with information all at once. But to truly appreciate how significant this is, we have to take a step back. Right now, the backbone of our digital world runs on laser light. Optical fibers, hair-thin strands of glass, crisscross the planet, beaming pulses of laser light that carry your Zoom calls, Netflix shows, AI prompts, and financial transactions. Each pulse is encoded with bits of data, and the more bits you want to send, the more light and the more bandwidth you need. That's where amplifiers come in. Just as a microphone boosts your voice in a concert hall, laser amplifiers boost the signal of a weakening light beam. Without them, your data would fade and fizzle long before reaching its destination. Amplifiers act as checkpoints in the system, making sure your information retains its strength and clarity as it travels thousands of miles. They are invisible sentinels along the data highway, amplifying the journey of light without distorting its message. Traditional amplifiers use a process called stimulated emission, where a single photon triggers the release of another identical photon. This preserves the signal's shape and intensity. But there's a limitation. The amplifiers only work across a narrow slice of the light spectrum, usually about 30 nanometers wide. That's like trying to fit all your traffic through a single toll booth. Effective for yesterday's needs, but hopelessly outdated for tomorrow's demands. Now picture trying to pour an ever-rising sea of global data through that narrow window. It's not sustainable. That's why the Chalmers team's creation is such a leap forward. The key to this innovation? Silicon nitride. This material, ceramic, heat-resistant, and incredibly stable, is the foundation of the new amplifier. It's already used in other microchip technologies due to its robustness and compatibility with standard semiconductor manufacturing, making it an ideal platform for integration at scale. But the real magic lies in how the team shaped it. Instead of laying out light pathways in straight lines, they used spiral-shaped waveguides. This clever geometry extends the optical path length within a compact space, letting the light interact more intensely with the amplifier material. The spirals enhance a phenomenon called four-wave mixing, an elegant dance of photons that combines multiple light frequencies to generate new ones, amplifying the signal while keeping noise to a minimum. Noise, random fluctuations that muddy a signal, is the bane of all optical communication. But with this amplifier, four-wave mixing occurs in such a controlled, efficient manner that the signal comes through clean, strong, and 10 times wider in bandwidth than before. Even more remarkable, the device is miniaturized. It's not some bulky lab setup. Multiple amplifiers can fit on a tiny chip, opening the door to compact, powerful, and low-cost laser systems that could revolutionize everything from cloud computing to smartphones. A telecommunications rack that once required bulky cooling systems and complex power management could now be replaced with a sleek panel no bigger than your hand. Currently, the amplifier operates in the 1400 to 1700 nanometer range, a sweet spot in the infrared spectrum that aligns well with today's telecom infrastructure. This range is known as the C+L band in optical networks, widely used because it minimizes signal loss in fiber optic cables. But the possibilities go far beyond that. Andrexon notes that with small tweaks, the amplifier could soon work across the visible spectrum, 400 to 700 nanometers, as well as broader bands of infrared light, 2000 to 4000 nanometers. That would open entirely new fields of application. In medical diagnostics, for instance, lasers are used for imaging, tissue analysis, and early detection of disease. A laser amplifier with broader bandwidth could make those images sharper, the scans faster, and the diagnoses more accurate. Imagine real-time, non-invasive scans that render tissue in unprecedented detail, enabling doctors to detect tumors while they're still microscopic. Holography could become more detailed. Microscopy could delve deeper into the cellular world. And spectroscopy, the science of analyzing matter using light, could become more precise than ever, detecting minute traces of chemical compounds in blood, air, or even interstellar dust. It could also advance optical computing, where data is encoded not in electrical signals, but in light itself. In such systems, speed is crucial, but so is the ability to carry complex information across multiple frequencies at once. The amplifier's extended bandwidth and low noise profile make it ideal for the types of dense, light-based processing that futuristic computing systems will rely on. And this isn't just theoretical. The research team is actively pursuing the next stage, adapting the amplifier for use with other light wavelengths and testing it across practical scenarios. They're exploring how it could integrate with portable diagnostic tools, autonomous vehicle sensors, space-based communication arrays, and more. It could play a vital role in disaster response systems, real-time environmental monitoring, or delivering ultra-high-definition imaging from deep space telescopes. It's a rare feat to create something that is both a marvel of basic science and a tool with real-world, transformative potential. But that's what's been achieved here, and there's something poetic about it too. Light has always been humanity's symbol for knowledge, connection, and speed. From fire signals on ancient hills to fiber optic cables under oceans, we've relied on light to reach across distance and time. Now, with this amplifier, we're not just shining the light, we're widening the beam. In an age where AI, streaming, remote surgery, and autonomous vehicles all compete for bandwidth, the infrastructure must evolve. And it's not just about speed, it's about possibility. The possibility of data networks that are leaner, faster, cleaner, of medical imaging tools that detect disease before symptoms show, of scientific instruments that peer deeper into nature's secrets. It's not just a better amplifier, it's an invitation to dream bigger. Imagine entire hospitals with imaging systems so fast and detailed that doctors can spot a problem before a patient feels the first symptom. Imagine satellite communication systems that can beam real-time, high-definition video from deep space with no lag, or quantum computing systems that communicate light-encoded information instantaneously between nodes. This isn't science fiction. It's the kind of future that becomes real when science stops asking how fast and starts asking how much. And that's what this amplifier does. It multiplies our capacity, not just in bandwidth, but in what's possible to imagine, build, and share. So the next time you ask your AI assistant a question, join a global video call or binge a sci-fi series in Ultra HD, remember, those invisible pulses of light might soon be traveling through a brand new kind of amplifier, one that makes the future 10 times faster. And this is only the beginning, because the real race isn't about how fast we can send data. It's about how much wonder we can pack into every pulse of light. Stay curious, stay inspired. And if you want to keep exploring the incredible breakthroughs shaping our world, one beam of light at a time, make sure to subscribe. The future is just getting started.